Hi everyone, and welcome to another episode of the AI Hardware Show. This is the after party, more of a free-form discussion of the episode you've hopefully just watched. If not, links in the video description. My name is Ian Cutress with More Than More, and joining me, as always, Sally Ward-Foxton, E Times. Hey,
Hello.
Sally.
Hiya.
Now, this episode, we've kind of archetyped this series as in, I focus a lot on the training hardware, you focus a lot on the inference, and yeah, this episode, again, kind of bouncy back and forth, but actually mostly inference.
Yeah.
A lot of the companies we covered in this episode, inference. And if you enjoy rants, there's going to be a couple in this episode, I can definitely tell you that. But you started with Aspinity, the AML100.
That's right. So Aspinity is very interesting, I think. A little bit like slightly different proposition to others, even at the very kind of far edge. So we're talking about microwatts, like 30 microwatts in operation. So it's basically designed to be switched on all the time. It's always on, but it like wakes up another part of the system. So it's like taking the always on bit from keyword spotting or from something else that you might be doing and just putting it like even further to the edge. Get ultra low power by just doing the whole thing in analog. Yeah. You know, signal kind of, you know, your sensor, everything is coming in analog. Don't bother changing it to digital. Feed it straight into like analog signal processing and then to analog compute and then, yeah, get a positive result and wake up something else.
Well, I mean, how many things now in our lives, aside from, say, the voice assistants, are just reactive to voice, right? Or it's all keyword. It's not keyword. Keyword spotting is two things. One is somebody talking. Two, is there a keyword? Yeah. And it's the first part.
So it's the first bit. It's the voice detection or the sound detection in your security system that is listening for broken glass or whatever.
That's the demo they have.
Yeah, so you can kind of, you know, hear that there's a sound happening and then maybe wake up something else to find out what that sound is.
But I think the point is it's a purposeful sound. It's not just any sound. So it's not activated by the wind, but it may be activated by the voice, as in it reacts to a certain frequency range.
Sure. Yeah.
And I described this earlier as the AI for your AI.
It's like wake up another AI to do.
Yeah, because it's a binary. It's like a binary yes or no. That's essentially, it does other things as well, but essentially the output is yes, turn on. 30 microwatts really is, we're talking about battery powered devices.
Even very small battery powered devices, yeah.
But it's speaker type going on.
Even smaller. You kind of IoT sensor type stuff.
Yeah.
With this, smaller than smartphones for sure.
Well,
like that very small.
Yeah,
very small.
And for something like this, right, everything's measured in terms of milliwatts. You can save a milliwatt here, save a milliwatt there. So if you can go down from what is your all-in-one combined wake word detection mechanism, which may be, say, 100 milliwatts, if it's always on, you go down to having this 30 microwatt
split out the
activation,
always on part.
And then you can have the other 99.9997 milliwatts is only turned on when it needs to be turned on.
Yeah, when there's somebody speaking, because most of the time somebody isn't speaking. And
doing that, it's an analog tool chain until that binary yes or no at the end, and that is their differentiating factor. I mean,
that's how they get it ultra low power. Yeah.
Some of these companies, only one of us has been briefed on because only one of us is right. This is one of the few where we've actually both spoken to them. But yeah, most companies, when they say they do analog, so the noise is obviously come in through a speaker, which is analog, but then that vibrates a membrane that creates a signal, which is digitized.
And then it gets digitized.
And then it gets reconverted back to analog for the compute.
So if you're doing analog compute, you have to change it from digital
to analog.
Back to analog to compute on it, and then back to digital
to find out what the result is.
Exactly.
Yeah. It's Schrodinger's analog.
Kind of.
And whereas these guys are just having the analog input.
Basically, yeah.
That's
just
where they're
use
saving
the
power.
analog input and then send it through filtering and signal processing, because usually it's audio. Send it through filtering and signal processing, and then do an analog compute on it using the same bit of hardware.
Yeah,
reconfigurable bit of hardware.
Which sounds pretty cool, and I think they're the only kind of people who are doing it this way. I'm sure.
So this is definitely something I haven't seen before.
Yeah.
Which makes it very interesting.
Or at least they're the only ones who have told us they're doing it this way.
Yes. If you are out there and you're also doing this, give us a ring. But no, it sounds absolutely fascinating. And yeah, the power figures are very impressive. And I think they've got a good use case. I think it's...
Yeah. The only question now is production price.
Well, there are a lot of other factors.
Commercialization.
Don't listen to me. There are a lot of other factors. But
yeah.
Analog kind of all the way through, I think is cool.
After Aspinity, I came to Intel's Greco. Now... I mentioned, at least in one of the episodes we filmed today, that Intel has a lot of products, right? They've acquired at least 3 AI hardware companies that we know of. At least one of those is dead. The other one is barely alive, and the other one is Habana. And Habana do training and inference. And in this episode, we spoke about the inference chip, Greco. So update from Goya to Greco. There's a theme here because the other chip is called Gaudi, so it's got to be a painter and it's got to begin with G. Basically, who knows what? Well, let's put it this way: they went from Gaudi 1 to Gaudi 2. They didn't go from Goya 1 to Goya 2.
Who knows why?
Knows? But the whole point here is we think it's the same kind of architecture as Goya because they haven't really said much about Greco yet. But it's, instead of a big 200-watt chip built on 12, 16 nanometer, it's a 75-watt chip on 7 nanometer, focused on inference, going in that Tesla T4, NVIDIA T4. They got rid of the Tesla name, didn't they?
Yeah, they did.
NVIDIA T4 A2 type, in that sort of realm where you can essentially put 20 to 24 of them in a big, large data center inference box.
Yeah.
And that they're still using TSMC, I believe. They're not pushing to Intel for manufacturing, but because it's under the Intel banner, Intel support, I think, with OpenVINO and maybe one API.
Not one API.
No, not yet.
Not one API. Not yet.
Not yet. One
Still
API
not yet.
was meant to be.
It's coming.
Yeah.
Still not one API.
So this, we're seeing a number of companies, especially the big ones, go after this sort of 75-watt inference chip market because there seems to be high demand. I remember speaking with Supermicro because obviously big system builder, they do lots of custom designs, and they're like, oh yeah, this is our inference box, and it's basically 2 CPUs at the front, 20 PCI slots at the back. And the idea is that none of them need extra power. They're all 75 watts. There are switches to deal with some of the mechanics of that. And I say, well, isn't there a bandwidth bottleneck anywhere? And like, no. And so some of these chips have built-in Ethernet acceleration as well. So there's that to contend with. And does it become like a SmartNIC or lots of different angles? But there seems to be a strong market for it for at least the big players. Yeah. And say what you will about Intel and whether they're cutting teams to realign their budgets, which, if you follow the financials, they've been doing some things along there. We just saw the networking switch division just be cancelled. So everybody's asking what's going to be cancelled next or sold. And one of the options could be the Habana acquisition, because one of the things they haven't been telling us about, whether it's Gaudi 2, whether it's Goya, whether it's Greco, are the customers. We know Mobileye is a customer, but Mobileye is Intel. Yes.
Well, we know we have Habana instances in AWS.
Yeah.
How many? We don't know.
And that's the big boy Gaudi 2 as well. So that's not this, for example. So
no, but this still counts as Habana customer.
Yeah. I do wonder with those instances, how many people are using them, and those metrics aren't publicized so much. Because if it's low, they don't want to make it public. But yeah, I got to see Greco tail end of last year at Intel's own event, at Intel Israel, when I visited in September. They also showed it off at Supercomputing. again, we still don't know the exact architecture, whether it's exactly the same as Goya, just scaled, or whether it's its own new thing. I suspect we'll probably see something later this year. Hot chips maybe, but Intel's presented chips at hot chips that have AI chips at hot chips that have subsequently no longer exist, and we'll get to that in a future episode again.
No longer with us, unfortunately.
Yeah. It does look nice though. They have made it look nice for a PCIe card. So
brilliant. That's what counts. So back to the edge, we're going to visit Kinara, formerly called Deep Vision, now called Kinara. So I think they changed the name to emphasize that they don't just want to do vision, although vision I think is a big part of what they are doing right now. So they're going for, robotics,
automotive.
Or no, I don't know about automotive, but certainly. So when I spoke to them originally, the big application that they were talking about was these smart retail and shelf cams, seeing what products are on the shelf, and then somebody takes the product. But yeah, you apparently need multiple neural networks running at once to make this work, the shelf cam. So that's one of the things they
on the camera or on the edge server that's in the back.
I think edge server for this.
Right. Okay.
Not necessarily in the camera, but you can apply it, of course, to robotics and to all other kind of things as well. We know it's a data flow architecture. I haven't had the architecture deep dive, but we know it's a data flow architecture of some kind. We know the software is super clever, can switch things around to make less memory accesses and stuff, but
trade compute for accuracy and speed and all that jazz.
So I went to Kinara's office not that long ago, in the autumn, and they have a super cool demo setup where you can see the chip running all different kinds of neural networks. So person detection, segmentation, pose estimation, all running on one chip all at once, which was quite fun. And I think I've got a photo of that you can have as well, in case you want to see it really working. But again, the setup was with the main application running on the NXP application processor, and we talk about it in the other segment. But yeah, you can if you're working on an NXP application processor and the AI part gets out of hand, gets too big during development, you can basically plug one of these in and then use the same software. So they work closely with NXP. NXP also works with Halo as well, just for completeness. Kinara and Halo is who you can offload to.
So is that it's essentially the same API is called in both instances, or is it the same architecture underneath? Do you know? Do we know?
I think the first one, API.
It's just a unified API between the two parts. I believe so, yeah. Okay. Because, so NXP does a lot of control systems. They recently announced the IMX 90 series. And I think it's
95.
95.
Yeah. So they have their own dedicated AI accelerator on chip, which is something that they've developed in-house for reasons.
Yep.
So there's something that's developed in-house, and they have a whole roadmap for it. They have a whole software stack for it. I think the setup is very good. But it's more about the size of it. If the application that you're developing just gets out of hand, basically, and you need more, you can add a Kinara chip then into the design, and it should be easy.
I think for some of these applications, having that ability to scale, even with inference, right? We talk about scaling and training all the time. Inference, when we speak about scaling, it's usually, how many instances of the inference can we do at once? At the same time, do we need to add more chips? In this case, it's just the size of one model gets bigger. You decide to have more weights because you need the accuracy. And it's important to realize that in a lot of these models, your trade-off is memory, compute, performance, latency.
Yeah.
And it's which 1, 2, or 3 of those do you prioritize over the others?
And if your balance isn't quite working out, or it's not working,
or you're running to a deadline, or or you've already got a stack of 10,000 chips in the back that you need to go through,
to use.
Or it's a cost. Would it be a cost? The thing is, if NXP doesn't have a higher end processor with more AI, you just need to slap something onto it. So basically,
So I think it's an interesting idea to partner with Kinara and Halo to kind of as an offload. I haven't seen that anywhere else.
It's surprising because NXP is a fairly well-known, well-established company in that space, but you got to wonder if it's just simply as if it's a revenue opportunity, or is there semi-seamless integration? How much work had to be done? Is there ongoing support? Yeah, that seems really weird, because sometimes we don't have vision into how many of these chips are used.
Yeah.
Right. I think this is the one you said are hyperscalers.
Yeah. So one of his customers for sure is a you said FANG company. So I'm assuming hyperscaler.
Yeah. Well, you also said shelf item recognition.
Yeah. So we have some ideas about who it might be.
Yeah. There is one of those companies that have lots of retail shelves or warehouse shelves that
where
need
it could be used.
Yeah. So that would be a pretty big win for a startup.
That would be an awesome win for a startup. And the word he described is shipping in volume to them. So I have to assume it's worked out.
Volume means different things to different people, I guess.
Very true.
Yeah.
Very true.
TSMC volume is 10,000 wafers a month.
Yeah.
But for some of these chips, that might be 250,000 chips for 10,000. Yeah, whatever.
We don't know.
So speaking of companies that have changed names.
Yes.
Just had Deep Vision to Kinara.
Yes.
This company used to be called ThinkEye, spelled THIN, capital C, capital I.
Not a great name.
I think enough people told them to change the name.
Yeah, they finally
They had to. The company is now called Blaize, right? As in, and which auto-corrects on my phone to Belize every time. BLAIZE, or ZE if you're American. And they have a graph streaming processor. And I think it's important here to recognize the graph aspect, because machine learning workloads, neural networks get compiled into graphs. And in order to accelerate graphs, you need the hardware that recognizes graphs. And it's not always just simply matrix multiply. Now we have, convolutions, transformers, intermediate compute in the graph, and how you partition the graph. So in order to work, you need a graph accelerator. So calling your hardware the GSP. I think even the Grok chip is called a GSP.
Yeah.
Then again,
graph core,
but all the GPUs and all the CPUs, and so there's a reason things have a name, and it's annoying that AI chips don't have a common name. There's some NPU, DPU, GSP.
Yeah.
AIP. I'm surprised nobody's done that one yet. They probably have AIU,
yes.
Artificial Intelligence Unit.
Yeah.
Edge, Artificial Intelligence. You could probably make some rather inappropriate words with these acronyms, couldn't you?
You could.
Yeah. We won't.
Or like XPU, well, that can mean anything.
Oh, yeah. The thing is, Intel says X to mean general.
Yeah.
There's at least one company out there that uses X for a very specific...
Yeah.
So Blaize, when it was ThinkEye, was actually one of the first companies to actually go to events to speak about.
They have been around for a while, yeah.
Been around for a while. So the fact that they're called Blaize and it kind of seems new, it's not. There are, but they've only really spoken about the one processor family that they've got, this GSP, and the whole point when the 2019 announcement is that they were able to take different types of parallelism that you can use in machine learning, essentially try and do all of them. So whether it's model, task, hybrid, workload, such that if you had any scaling problem, whether that's multiple networks on one chip or one network that goes across multiple chips or anything in between, or even different workload variants, say memory requirements, they have the compiler to do it all. Now, I have a problem with companies that say they have good compilers. Nobody ever has a good compiler.
Not ever.
Not ever.
Right.
If you think you can solve your problem with a compiler, you can't.
But you need good compilers to make it work well.
Yes, you need good compilers.
It's really, really important.
There are no good compilers.
Okay. Blanket statement.
arguably you could say it should be easier in the machine learning world because machine learning should be well defined. Unfortunately, we're in such a period of rapid advancement right now, and I bring up constantly that we used to have convolution neural networks, especially for vision. They were good for vision.
Yeah.
And that was the rage 3 years ago. Now it's all about transformer networks.
Everything's about transformers.
For natural language processing.
And vision.
But if you focus your chip on convolutional neural networks, it's no good today because you can't do transformers.
Yeah. So
you do a transformer chip today, perhaps you miss out on the next wave.
So you have to have that level of flexibility.
Yeah.
Otherwise, you've seen how fast things evolve. It's a balance of flexibility and performance, though. So it's a difficult question.
And the companies that are kind of losing out are, the ones that have announced layoffs, haven't had a new chip that does specifically, say, transformer networks recently. Optimized for transformer. They're optimized for convolutional, but not for transformer. So they're not getting any customer base. And I think with Blaize, they need to be a bit more upfront about their roadmap, where it's going, what the deployments are in. The white paper, for a company that's been around for a while, and the chip's been out for a while, their technical white paper was unabashedly non-technical. Right, and it's called a white paper. You got to be technical. Come on. So I think this company has to showcase technical prowess and a roadmap to be considered a serious player.
Yeah, I think as such an early entrant, you kind of want something to have happened by now. Yeah. So I know they were working with automotive industry.
Working with automotive.
So I know we've spoken about this in the last episode or in the last couple of episodes, but automotive is really, really tough. So I think they've had to go after other applications as well, and they've also tried to make their software stack into a product kind of in its own rights, which I'm not sure about that as a concept. Whether it's any good or not.
You have to be
I don't
dedicated to it.
Well, it's a difficult play. So I think they're trying several different things. But yeah, with a company of this age, you'd want something to have happened by now.
But the one good thing is they changed their name.
At least they changed their
name. So we've already covered a number of companies that we can't say the name correctly in this series, whether that's Moffat.
The Chinese names are
Enflame,
difficult for us. Yeah.
Enflame. Yeah. There's a couple more coming. This one is just spelled wrong.
Yeah, EdgeCortix.
Cortex.
Not Cortex.
We'll put on the screen what and we were debating. Right, if you search for EdgeCortix on Google, you get the EdgeCortix.
You get EdgeCortix.
You get EdgeCortix, the company. And whenever I hear something like Cortix, especially if it's got a word before it, like Edge, I think of Neo Cortex, the boss in Crash Bandicoot.
Cortex to me only means ARM's product line for microcontrollers.
And I think your explanation of this is actually, the reason why.
Yeah, I wonder if they were called EdgeCortix, and we are speculating whether ARM have been in touch.
Yep. Hey, excuse me, that's taken.
Yeah, that word's taken, and has been for a long time.
Well, if you don't defend a trademark, you can lose it.
So they're called EdgeCortix anyway.
Mind you, Edge in itself in video game industry has been a trademark that's been. If you've ever watched Guru Larry's videos on Edge, they're quite funny.
So EdgeCortix. EdgeCortix. They have this reconfigurable thing. They have this reconfigurable data paths, and they have different types of compute units, and they kind of reconfigure kind of around them. The compute units can be bigger and smaller and so on. So it's about flexibility, I think.
So it's not FPGA.
No.
Is this a CGRA configurable?
It could be something like a CGRA.
Coarse-grained
reconfigurable architecture. Or coarse-grained reconfigurable array.
Or architecture, yeah.
Yeah. And so it doesn't specifically say CGRA in their material, and I think it would if it was.
So the big CGRA player that most people like to talk about is Samba Nova.
Yeah.
However, there are, I know, smartphone companies who don't talk about their AI solution, but if you read between the lines,
it's a bit CGRA-like.
It's a bit CGRA-like, and this kind of sounds like that.
Like it might be because it's kind of reconfigurable. Reconfigurable has a specific meaning in hardware, so I think maybe we're going down the same line there.
It depends whether it's a fixed pipeline or a diversion pipeline, because again, Samba Nova CGRA is the idea that you can, if you need to do the same operation, you can kind of cycle around elements to get your essentially get your compute within a given area. Whereas if it's a fixed pipeline, your data is only going in one direction.
Yeah.
So.
Yeah. So for EdgeCortix, I think they want to be an IP company. They're making a chip, one chip, at 40 tops and 10 to 15 watt TDP. So I think this could be a seeding the market type operation, waiting for
like an M.2, 15 watts is about M.2.
15 watts is about M.2.
Edge, inference.
Kind of as a demo of what the IP can do. I think 40 tops is about as big as you'd want to scale this IP. You'd want to probably scale smaller. I guess we'll learn more about EdgeCortix as time goes on and as they release more products. So let's see what happens to them. But so far they've announced they're attending defense shows, and maybe they're into defense and so on.
Samba Nova's into defense though, so maybe they're trying to piggyback off.
We don't know. We don't know. It'll be interesting to see what happens to them.
It's in this space. I do worry about pure play IP companies because there are so many chip companies out there, all with different levels of IP that could arguably just sell IP. So it kind of feels like you're only. I don't think long term you can sell chips and sell IP because you're kind of competing with your own customers in a way. You kind of can to SoC makers, which is a slightly different play, but I think it's going to be difficult. You either have to be an IP or a chip company. In the words of Ron Swanson, whole-ass one thing. Don't half-ass two things.
Yeah, I guess so.
That's fair enough, but yeah.
I mean, it's a completely different proposition being an IP company. In terms of the resources you need, the funding you need to raise, the timescales you work along, like it's a totally different play.
Your customers get more aggressive on frequency of updates, whereas if it's a chip, it's ready when it's ready.
Yeah, it's ready when...
An IP is what's taking you so long, you don't have to tape this thing out. We do.
But there are quite a few IP companies in this space, half a dozen at least, I'm following, that most of whom we're not going to talk about in this series because it's really supposed to be about chips. But some have pivoted from being a chip company to being an IP company for various reasons.
It's expensive to make a chip.
It's very expensive to make a chip. Yeah, there's a lot of competition right now, especially at the edge.
So, I mean, the final chip we covered in this episode, again, if you haven't watched the episode, links in the description. This was an interesting one to me because I came across this chip years ago. And I told the story in the episode of how wandering the halls of supercomputing in Denver, 2019, the last supercomputing I actually went to in person. I can't wait to go again. Back then, as a journalist, I was looking at things to write about, and we'd seen all the fancy stuff had been announced at the beginning of the show, and Intel has had its HPC event, and here's the Japanese section, and at these shows, sometimes there'll be like the Japan sponsored booth and the French sponsored booth, and because it's supercomputing, high performance computers. There are obviously groups of universities, pop up and say, let's have a little booth and just show off the university research that they've done. So you get a lot of research papers, posters. They essentially condense everything down into a poster, and usually the person's on hand to answer questions if you have any. And I was just going by one poster. I can't remember whether it was specifically their booth or part of another booth, but it had a random picture of a chip. And of course, chip, tasty. And it was a chiplet-based chip in 2019. So we'd already used to chiplets in that context at this point. But it was 4 massive chiplets, each one about 700 square millimeters. The whole chip used 3,000 square millimeters of silicon, and it said 500 watts on the poster. I'm like, huh. And it also had like a diagram of the architecture. So you had this compute unit, and 16 compute units shared an L1 cache, and then 16 of those had an L2 cache, and then 4 of those had a chip, and then you had 4 chips, and there's your card. And then it also showed a render of what a finished package on a card would look like. And it's this triple slot PCIe monster with a massive blower fan, and you're thinking, PCI card, 500 watts, huh?
Hang on a minute.
Yeah, that's a lot to put in a PCI card. Now, in 2019, we're talking about, right? Today, you buy an NVIDIA 4090, you can crank it if you like. They go up to, 450, 550, keep going. But, and then, so I wrote a little story about it, and I tucked in the story that, it was optimized for FP16 or half precision FP16.
Yeah.
Which in HPC isn't high performance computing, so scientific research isn't an uncommon. It's an uncommon data type, but it's not unheard of.
Okay.
Right? Normally, you work in double precision 64-bit or single precision 32-bit, and so I filed it away and put it in the back of my head and didn't think anything of it. And then it turns out in 2021 they put a large number of these chips into a supercomputer that was about 4 petaflops. And right now we're at like 1 exaflop, so it's 250 times smaller than that, but it's still a supercomputer, and it turns out to be number 1 on the Green 500 list. And so this is the MN core chip, Preferred Networks, and the MN3 supercomputer. Now, Preferred Networks is, I initially thought it was like a university spin-out that had just started producing optimized silicon for the Japanese university system, because not only with MN Core, they have things like MN Grape to do with, I think that's molecular dynamics focused, and there have been 5 generations of that or something. And
cool.
The whole point being optimized silicon such that you can create research papers.
Yeah.
If you ever heard of Anton from D Shore Research, it's kind of the same thing. But it wasn't until going back and researching for this episode, it occurred to me the FP16 format supported really good for machine learning. And what's the supercomputer used for now? Practical machine learning. Now, these cards, like I said, 3,000 square meters of silicon, this triple slot, double height PCIe card as well, custom blower. You put 4 cards into 7U. How many NVIDIA GPUs do you think NVIDIA try and fit into a 7U?
Yeah.
Right?
Yeah.
At least 8, if not more.
Yeah.
And because of this card, there's only 2 x86 CPUs in a 7U system, and their supercomputer is essentially 3240 of these 7U systems altogether. So there's a lot of silicon, a lot of chips for something that not a lot of people have heard of, and I first saw on a random poster at Supercomputing.
On a poster.
So yeah, it amazes me how those are the stories I like to talk about in the industry, where you caught a glimpse of something ages ago, and it didn't fully, because it was then and not now, you couldn't have processed it in now context.
Yeah.
And then when you process it in a now context, the vector of how you thought about it changes.
Definitely.
And that is one of these times.
Yeah.
They did say that there's going to be an MN4 supercomputer with MN Core 2, and it said operational by the end of the year, of the fiscal year ending January 24.
Okay.
So 23. So supercomputing is in November.
Hopeful.
Yeah. So we should hear about MN Core 2. And if anybody from Preferred Networks ends up watching, give us a shout. Email is on the About page on YouTube, because when you want to start talking about it, we want to start hearing about it.
You know where we are.
But yeah, it's just an absurd. Is it TSMC 12 nanometer? I can't remember. It's definitely like 12, 14, 16 nanometer, that sort of class of family. I know. Whenever I hear 12, I instantly think of Global Foundries, and I don't know why.
Why?
I don't know.
Why?
I think we alluded to this either earlier this episode or in a slightly previous episode. Those big chips on sort of that 12, 14, 16 processes, it's now getting to a point where smaller startups that are getting, the low tens of $1 million of funding can happily produce big chips on those processes within that budget.
Yeah.
And a number of the first generation training chips, especially that we're seeing in the space, do just that. TensTorrent, Blaize, plenty of others. So I don't know. I want to hear more about what MN Core 2 is, because the MN Core 1 seemed pretty simple, right? It's just let's do lots of compute units for HPC that ended up being good for machine learning. Is MN2 going to be more machine learning focused or HPC focused?
They're more deliberate in the direction of machine learning, I think. Could be really interesting.
Or supporting things like FP8 or configurable FP8. And, there's a whole discussion on quantization. Yeah. But yeah, no, I really enjoyed this episode. A lot of edge, and then just a fun memory actually coming to
at the opposite
blooming,
end of the scale. Yeah. On the Green 500, it's like literally the opposite. The tiny bits of IP that we're talking about. This is the joy of this show. They are totally different.
So in this episode we covered 30 microwatt.
Yeah, it's a supercomputer
to 600 watt chips. That's okay. That's several orders of magnitude.
It's the whole spectrum, basically.
Bottom to top.
Yeah.
So if you like this episode, if you enjoy watching the show, please like and subscribe. There are links in the comments below to not only the other episodes, but also Sally's content on EE Times on some of these chips. And if you enjoy it, say so in the comments, but we'll see you on the next episode.